All right, I think we'll get started here. It's my pleasure today to introduce Christian Gross from University of Tübingen. Christian, really needs little introduction. He did his doctoral work in Heidelberg in the group of Marcus Oberthaler, where he performed groundbreaking experiments demonstrating a BEC-based interferometer with precision below the standard quantum limit. I have to say, these are papers that I actually recall reading and being quite excited about as a graduate student. After a very stellar PhD, Christian then went on to MPQ in the group of Emmanuel Bloch, where he led many super exciting experiments on a variety of topics, ranging from many-body localization to transverse Ising models to light matter phenomena to fermionic quantum simulation, and this list really goes on. The breadth and productivity of the work during this time was just amazing. He's been recognized for numerous awards, including an ERC in support of his work building his own group now at Tübingen. I realized I could end on a poetic note here. I realized in preparing Christian's intro that he is in fact the last person that I introduced for a seminar in person. As we are well past here now, I really hope that you are among the last that I introduced virtually. So thank you for being here, Christian. As a reminder, you may ask questions in the Q&A on the Zoom or in the sort of chat indicated on YouTube. Great. Christian, why don't you share your screen and take it away?
Yeah, while I'm preparing the sharing, thanks a lot for that very kind intro. And I think it was a completely overwhelmed intro. Yeah? So thanks, Adam. And yeah, actually, I also noticed just last week, just to ask before, sharing is working? Yes, right? Okay. I also noticed just last week that it was actually my last travel and my last like really true talk, like with an interaction that is really an interaction, yeah, with you guys. So that was truly a very nice experience, and it was a good last, like that can last 1.5 years, yeah, but it shouldn't last much more longer, as you said, right? So okay. So today I want to take you actually through a tour of our results and also a bit results of others of the analog quantum simulation of the Fermi-Hubbard model with a focus. Well, obviously I talk a bit about our results a bit more than others on actually measurements regarding spin and density cross correlations. So that's where my title is from. And so let me start giving you a motivation and maybe also a little very quick explanation of the mindset of quantum simulation. And let me try this drawing trick here. So let me first give you really the idea how you can imagine what quantum simulation can be good for and in which way it can work. So let's assume you have some block of material that you don't know anything about. It's a very complicated material, but now you cannot describe it, you cannot model it, and especially, or maybe you can model it, but then you cannot solve the model because of it's a strongly correlated quantum material. Yeah. So what you, as I said already, what you do first, you somewhat model this material model. But again, the problem is you cannot solve it on your computer. And now, but if you have your nice quantum simulator, you might be able to implement that model actually on your quantum simulator, which for us are ultra cold atoms trapped in an optical lattice. That's why I draw points here. And now say, okay, now I can do some simulation of that model on my simulator. Then of course, what I have to do, I have to measure. And then I draw conclusions, but I then draw conclusions and feed these conclusions back into my model, right? And then I somewhat loop that and try to learn how my model behaves. And then I might be able to do another roll of feedback and try to understand if my model, maybe with a slight of experience here, if my model is actually good to describe that actual material. Yeah. So in this sense, you can understand how quantum simulation might give you in the end useful information about a very complex material. And important to mention is here that I think it's beyond hope that we really can simulate ever that material in all its details, right? So there's always these modeling steps, and there are always these inference and arrows that I've drawn here. So that let me give this you as the general intro, and now jump a little bit into the details. And the details will be all about the example of the quantum simulation of a Fermi-Hubbard system. And what I show you here is basically in this picture is, let's say, the best guess, let's say like this, because not everything is known down here. A lot is known. Most of this is known. It's a very good guess, but really not everything of the phase diagram of the 2D of the Fermi-Hubbard model, and that's what's it about today. The Fermi-Hubbard model can actually be very nicely modeled with ultra-cold fermions and a very advanced quantum simulation tool for those or with those ultra-cold fermions that came about since 2010. Then it was bosons, and 2015 fermions is the quantum gas microscope. And I show you here basically a set of pictures from, actually the pictures are from those groups that have those microscopes now simultaneously with cold and correlated systems. So that makes the selection for the bosons. So it's well, I don't go through all the groups. You can read that here. And for the fermions, and these why this is a cool tool, because of this tool gives you basically single site detection, a single atom observation with really near unity fidelity, and the tool gives you at the same time basically single site control of the density and of the spin of the system. And I really want to mention there are more microscopes that are running, and the microscope part of it is present everywhere. Some of them are still working on getting things cold, but there's definitely a lot of work in other groups in this direction. And maybe I mention especially these very young groups of Peter Schaus in Virginia and Takeshi Fukuhara in Tokyo, I think, somewhere in Japan. I don't remember now. Good. So this is the tool we are using, and the tool, as any modern microscope, as any modern AMO setup probably, or as many modern AMO setups, it doesn't look that simple. So what you see here is actually two pictures of the two optical tables we have at the setup at MPQ. Maybe I should say that. So Adam introduced me on being in Tübingen. I just changed to Tübingen, right? So all the results are here from what we obtained at the MPQ in Garching. So what you see here is basically pictures of those two optical tables. On one table, we prepare all the light, and you see this forest of mirrors. We guide the light through optical fibers. So this stuff here from one mirror, from one table to the other table. And on the other table, we have our main experimental chamber with all of these nice microscope techniques. And basically, you see nothing. The atoms are somewhere here in the center. The microscope is somewhere here from the bottom, looking onto the atoms, but much more you don't get from here. So let me simplify this setup a bit for you. So this is the simplified version of the setup. What this setup does, it prepares a single atomic plane in the ultra-high vacuum chamber. And then basically there's a high-resolution microscope from the bottom. We use laser light, specially tailored laser light, to somehow cool the atoms while the atoms are scattering, such that they can scatter many photons, so in the order of 50,000 or so, before they hop from one side to the other. Well, actually, they basically never hop. The hopping probability should be somewhat below 1% or something. And then basically you collect the fluorescence, and you get images like shown here, where you can really identify in that atomic plane each and every atom as an optical signal on the detector. Yeah, and again, typical detection fidelities are somewhere 99%, so something like this. Yeah, takes actually if you are densely packed, then it takes quite some time actually to collect such an image. And these microscopes, I talked a bit about the technology. They really were a door opener for many new experiments. And there's really a long list of amazing results that came out of these machines. And let me give you a few physics highlights. That's just a selection, and I actually selected from being orthogonal to what I will talk about the rest of the talk. So There have been a set of very nice transport measurements in the Fermi-Hubbard model on spin transport in Martin Zürlein's group, and on charge, on density transport in Wasim Bakr's group, where they studied basically the reaction of a spin imbalance or density here, density wave, for different parameters of the Hubbard model. Another set of experiments also out of equilibrium experiments, but these are really very far from equilibrium, where these first experiments are more close to equilibrium, where people studied thermalization. People is we and the Greiner group, Marco's group in Harvard, studied far from equilibrium thermalization dynamics, and tried to observe many body localization, and observed strong indication of many body localization in these systems. And I said what I highlight here is orthogonal to what I want to talk about today. And today I talk about the Hubbard model in equilibrium, or almost in equilibrium, and we want to take a new look on the interplay of spin and charge in this model. And I said that already. How do we create those Hubbard models? We make them basically by optical lattices. These are crystals of light that we create by interfering laser beams. We typically interfere basically laser beams from all three orthogonal spatial directions, and we create a crystal of light. And I said before, we prepare the atoms such that only one plane, this I cannot draw now anymore in this picture, that only one plane is basically populated with the atoms. And then we sprinkle in our fermions. We sprinkle in mobile quantum particles. And then these fermions of two spins, red and blue, right? They can hop around in this one plane that we select, yeah, the hopping goes with the T, and they can interact with the U. And I should say almost all incarnations we have so far have on-site interactions U, with one very recent notable example, I think, from Wasim Bakr's group, where he used Rydberg coupling to actually induce a nearest neighbor interaction also. Yeah, and with this we get our nice quantum simulators for some strongly correlated models. Let me give you now the concrete outline of my talk. So what you see here is again the phase diagram. This is actually a phase diagram for cuprates. It's not the phase diagram for the Fermi-Hubbard model. I should say that to be a bit more exact here, basically. And I gray out here a region because I want to also tell you a bit what are our big grand challenges in this game here. Yeah? So at the moment, actually, the really low temperature region is not really accessible to our AMO machines because of it. On the many body scale, we simply don't get yet cold enough, even though we always call ourselves, of course, ultra cold, right? So where we are somewhere at this upper, just on this upper border of this grayed out area. And the experiments I want to talk about today, they are basically studying the system in the single or individual dopant limit. So basically, I should say what it is actually on the axis. So what you have here is the whole doping axis on this phase diagram. So basically here you have every site filled with a 50-50 mixture of spin up and spin down fermions. And if you go to the right here, you're reducing the number of fermions in the system while keeping the balance. So it's always a 50-50 mixture. And on this axis, I said already, is temperature. So we are talking about experiments very much on the axis with only very few missing fermions, so few holes in the system. We study this in 1D and 2D. We talk about equilibrium experiment, and in 1D, one little dynamics experiment. Then we also talk about, in 2D mainly, also a bit in 1D, but we do everything for 1D and 2D actually. We talk about the doping dependence. So we move actually along this line from the strongly correlated Hubbard model to effectively a Fermi. Maybe you can read this here basically. So to basically a Fermi liquid, and we study system correlations and characteristics through that arrow here. And of course, in AMO system, it's very easy to move along here. We just load less atoms into our lattice, right? So this is basically just you change a number from 10 to 3, and you have less atoms. Good. So let me start with 1D experiments, and let me show you the first concrete images for that. And let me tell you about the secret that we have in our lithium machine at MPQ. And the secret is that we have spin and charge resolution at the same time. So what I show you here is basically a picture of a 1D chain of fermions. And actually, this is one 1D chain, another 1D chain, and so on and so forth. And this is an image that is just resolving the density. You see each and every atom. These are actually 2 atoms. What we can now do is we can do like a local Stern-Gerlach splitting before we actually raise super lattice potential. So with 2 wells, as you see here, basically, in the vertical direction, splitting each of those lengths basically vertically in 2. And because of the magnetic field gradient, this forces the spin up atoms to go to the upper side, the spin down to go to the lower side. And with this, we basically get a 1-to-1 identification here, right? Of basically all the all the occupation in density on spin for all the sides. So this is a bit the specialty we have, and you will see 2 more incarnations of this technique. So this is the 2016 version 1.0. I will show you 2.0 and 3.0 throughout the talk. Good. So let's start a bit with the simple physics of the Hubbard model in 1D and at half filling. Half filling is the thing that I explained you, exactly same number of fermions, 1 atom per side. And in this limit, at strong interactions, we can actually, maybe I showed this already, one can map actually the model to an Heisenberg antiferromagnet, as shown here. So we can map this complicated Hubbard model to a much simpler spin model. And it's an antiferromagnet. Why it's an antiferromagnet is very easy to understand actually with my little comic here. So assume you would have a ferromagnetic ground state. You would have like a block of 3 equal spins. But now if you look at the middle spin has no chance even to slightly delocalize to the sides because of that is Pauli blocked, right? But now if you look at the other combination where you have actually a downspin in the middle, this has the possibility of balancing a bit the interaction energy it has to pay to basically delocalization energy it wins, which is allowed because of it is not basically Pauli forbidden to go there. And this gives you already the idea that basically the antiferromagnetic combination here is the ground state. And this is what you also get when you do the Heisenberg mapping here. So this gives you a bit of intuition why this is actually an antiferromagnet. And if you're then in the spin language, then you see basically there's an atom on each side, but of course now the spins can still move. And the spins can move by a super exchange process that is basically as shown here. So this blue guy hops on top of the red guy, and now the red guy hops away, means 2 hops. So 2t is a t squared basically process, and it costs basically this penalty u, right? So this gives you the energy of the super exchange. And now we have all relevant energy scales in this model. It's the t, it's the j, it's the u. Yeah. And we can study the Hubbard model 1D at half filling, and we did that in our microscope. You sometimes see very nice shots where basically the whole system of something like a 15, I think here, atoms is fully antiferromagnetically ordered. And you see it also because of your projected on the z-axis, but it's an SU2 symmetric thing, right? So this is even if you're at t equals 0, this is a rare shot. And then we measure that basically by in this case you will see many more correlation function. In this case, it's just a simple 2-point correlation function, and then we see the antiferromagnetic characteristic, right? So on side distance 1, we are the sign is negative of that correlator, positive, negative, and so on and so forth. And you see already a sign to what I said actually, that this system is rather hot. Because of the correlation length, maybe you see this in this exponential plot. Somewhere here is 10 to the here's somewhere 1/3, and that 1/3 is somewhere between 1 and 2 sides. So the correlation lengths are never really long. And in case I use accidentally the word order, you always replace it by correlation in the talk, because of everything here is warm and correlation lengths are short. Good. Let's make the thing a bit more complicated. Let's add a few holes. And let me now talk about the 2 sectors, basically the density sector, which I used to call charge sector, hopefully consistently in the talk, and the spin sector. So if you just think when you have a hole, what does the hole wants to do? The hole wants to delocalize, right? Because of this minus t here. So that's indicated here by the shading. What does the spin wants to do? Well, the spin we discussed wants to be antiferromagnetic. The question is now, if we have a hole, can we make the hole and the spin sector equally happy in one dimension? And the answer is in 1D, yes, you can do that. You can do that by basically having basically antiferromagnetic correlation across the hole, which is, by the way, opposite as if there would have been a downspin, right? If there would have been a downspin, those distance 2 spins would be aligned, but if there's a hole, they are anti-aligned. Why? Because of then you can delocalize the hole and you never pay an energy. If you do that in this case, you move the hole, then you get 2 upspins and you pay J. Right, so this shows you already that in 1D, actually, there's a way of making spin and charge degrees of freedom at the same time happy. And you will see that this is actually the origin of basically that they don't care for each other really in 1D. That's spin charge separation. We can study this. So let's now go to 3-point correlators. So this is first the normal tic-tac thing I have shown you before, but now we can basically measure the correlation here basically selected on having a hole in the middle, and you see the correlation turns completely around, and we see actually that opposite sign of those spins if there's a hole in between. That's a very near short distance measure, and I want to show you basically now that we can also get longer range correlations back if we use more complex correlators. Let's first think what happens if I use a standard 2-point correlator. So don't even look at the formula, it's just a standard 2-point spin correlator. Let's say I want to measure correlations between spin 2 and 8. And if everything is filled, that might be a nice correlation. But now if I have holes in between, then we saw basically that always changes basically this spin alignment of actually the whole sector of collected spins of spins that are together that comes behind. And now if you have a fluctuating hole number, that basically messes up the correlation. But there's a way of revealing this. And the way of revealing is by using non-local string correlations. Because you know what the hole does, it just basically flips all the spins that come after the hole. So what I can do is I can just measure a string correlator that goes through all the chains. And since we have through all the sides of the chain, and since we have full counting statistics, we can do that in post-analysis and take each hole into account with a -1, basically flipping the spin alignment that we expect after the hole once upside down. And with this, we can basically take those holes into account and try to recover the spin order. I should say, I mean, this string order parameter is the same thing that would detect basically hidden topological order in spin 1, for example, in the Haldane phase. And that was brought up for fermions in 1D by Jan Saanen in the early 2000s, actually, here in these papers. And now again, can we measure this? First, now we move a little bit on the doping axis, right? So what we do now here, we prepare 1D chains with a few holes in them. And what I show you here is the signal of the standard 2-point correlator. You see nothing. You see nearest neighbors are anti-correlated. That's just Pauli hole, but then no sign of any correlations anymore. And let's analyze the same system with the string correlator. And you see basically we are getting the same tic-tac behavior back that we had before with the fully filled systems without holes. And we could really put it on top of each other, and you will see that the curves are basically indistinguishable. And that shows you basically that really the spin, if I analyze it with the right observable, doesn't care really that I have holes in the system. And this is kind of an incarnation in measured with a weird multi-point correlator of spin charge separation that we measure here neither in the spectral quantity nor by some dynamics, but just by analyzing fancy correlators in that system that are enabled by quantum glass microscopy. Yeah? And I guess this is a good point to stop, I guess, Adam, to ask if there are first questions on this.
Great. Yes, there are some questions coming in here. So let me start with one that's a pretty general question, which is you had this nice description of how the cold atom experiments really fit into the broader context of material physics and specifically the Hubbard phase diagramming. So what is needed to go below the sort of analog of 300K using a cold atom system?
Yeah, that is a good question. I will actually come to that. In the last, I will at least comment it, but I can do it also now. So what is needed? We need a way to get spin entropy out of the system, because what remains is basically spin entropy, mostly spin entropy there. What actually is the so we cool by evaporative cooling, and what happens is actually at least in all the I think it's in all the microscope, they do the final cooling now, all by a spin mixture, evaporative cooling, and it's known that this technique becomes very inefficient around 0.1 TF, because of basically you get a Pauli blocking of the collision channels. That's the problem, which then makes the cooling inefficient. And I think the microscopes is always a bit hard to compare the lattice temperature in the strongly correlated lattice systems to bulk systems and so on and so forth. But we are roughly at 0.1 TF, I think. Record temperatures in bulk systems cooled sympathetically are at we are 3 or 5%, so factor 3 to 2 colder by sympathetic cooling with a boson. So there's a hint that this works slightly better. And there's another trick of getting colder, and that is by using entropy engineering, by basically by local manipulation of your system, basically bringing your part of the system that you're interested in into contact with the reservoir system. And the reservoir can take a lot of entropy, effectively cooling basically the part of the system that you're interested in, and that has been realized in Markus Greiner's group in his microscope, and that has been very recently also realized in Jan Weipan's group not under microscope but also in a lattice system. So it's only the detection which is different, and there are very promising results from this direction. Great.
Let me ask one more general question, and this is sort of perhaps a sort of personal perspective question too. So the question is, do you think that cold atom quantum simulation is best for studying and explaining real materials, or for realizing entirely new kinds of materials, or is it sort of both?
Okay. The realizing entirely, so my personal perspective, let me also answer from a personal perspective.
Yeah.
It's of course a little far-fetched calling these things itself a material, right? I mean, this thing lives in a laser. As soon as you somewhat come close, it implodes. So that's why I'm a little bit hesitant of calling this thing a material. It is of course mimicking a material, right? So of course it can mimic new materials that are not existing, and you can use that to explain or to uncover or single out or crystallize out, or however you want to call it, a nice quantum many-body effects, and with this shed new insight on basically quantum many-body physics or test models or whatever. This you can really imagine to do, and that is what we are doing right now at this stage, right? So to really simulate real materials, I think what we need is a little bit of more programmability of the system, because of what we have here is, I call that the Fermi-Hubbard model, but what it is the simplest Fermi-Hubbard model that you can have. On-site interaction, nearest neighbor hopping. That doesn't really model a real material. For the real material modeling, you need a few more parameters. You need nearest neighbor hopping. You need maybe a nearest neighbor interaction. Maybe you need nearest neighbor hopping and things like this, right? So this bit of programmability, maybe unit cell engineering in some sense. I mean, this we do already, but more complex unit cell engineering. And I think then we are not that far away of actually giving useful insight also for models for materials, right? It's never for, I'm really strict with this, models for materials, because I think if you say you really model one-to-one a material, that's quite a future dream at the moment.
Got it. Thanks. Okay, there are a couple more here, but let's keep going.
Okay, good. So let me jump to the next part. The next part basically now is my little excursion away from equilibrium, and that is about that is connecting to the story of spin charge separation that I was just telling you that we detected by correlations. We also, these cold atom experiments, they are nice in the sense that the dynamics is slow and that you can follow basically in real time, in a sense, the dynamics. And this is what we do now to uncover spin charge separation, really as a separation of wavefronts or of a spin and the charge excitation. And that is basically following those two proposals here, both from Willi Zwerger's group. So the idea is we prepare basically this 1D chain. So this is one chain, this is a time. So we prepare one chain and at t equals 0, we kill this atom. This atom carries a charge, it is an atom, right? It carries a density. And this is also has a spin, of course. So by killing this atom, and we kill that by shooting a laser beam, we are inserting a spinon and we are inserting a holon into the system. And now the idea is to track that spinon and the holon. And of course, the catch is that's not so easy because especially for the spinons, there are quite some spinons in the game. I showed you that correlations lengths are short, right? So here's to show you how good we can do that. So this is our chain, and you see there's no atom on that side. Then of course we can do statistics, and then you see basically, if you trust my color scale, right, you can always cheat with color scales, but I think this is even an honest color scale. We kill quite well one side here. And then we let it go. Maybe a little comment for the experts. Maybe you have heard of that that the 1D Fermi-Hubbard is actually a general Luttinger liquid, and that what we are doing here is we are not studying the system in the Luttinger liquid regime, because Luttinger liquid is all about the low K excitations. But when you kill an atom, an atom, and kill an atom on an individual site, that is, of course, intrinsically a very high K. It's fully localized, right? A very high K excitation in the system. And here you see basically what we get. So you see basically in blue the density signal, and in red you see the spin signal. And let me not tell you much more now on this, but just highlight these times. So first you see basically to spread out to like 3 sites distance here, we need 4 hopping times, or 4.7 on 18.85. You see the spin is much slower. I can also show you that scaled basically by Scott squeezing these 2 plots. And you see the hole has already reached basically the edge of the system, while the spin, well, has not even noticed that there was a hole shot into the system, right? So there's really a very strong separation of timescales here. And of course, we can also show this. So this is now basically tracking the width of those distributions you have just seen in this 2D plot versus time. And you see basically the fast hole and the slow spin here. And you see really that those 2 excitation wavefronts of the spin and the charge, they really dynamically separate. And I think it's a bit early for the next break. Let me jump over to 2D and maybe make the break for the first part of the 2D. So this was the story of 1D. So we had the story of very individual holes, more or less, and then a little bit of doping, and we had this basically spin charge separation in different pictures. Now we tried to make the same picture in 2D. So let me try to make you the same sketch that I have done in 1D in 2D. Maybe one remark, it gets now a bit messy. I try to squeeze all different experiments in one. In 2D, we do experiments once with a doublon. The model is doublon hole symmetric. Just think of it was a hole, and you can ask me in the end why it was a doublon sometimes and sometimes a hole. So we basically imagine we have a doublon on one side, and we have a perfectly antiferromagnetically ordered background. And now the question is again, can we make spin and charges somewhat simultaneously happy? And we try this motion again. And if I now move basically, so this is a spin up and a spin down, right? So let me move the spin down to the right, the spin up stays. Then you see I get 3 wrong magnetic bonds here. If I move it further, I get again 2 more wrong bonds here. And it turns out actually that you cannot find any combination of whatever spins that let this doublon actually move away. And what I assume in this picture is, of course, that the T timescale is much faster than the J timescale, because, of course, I mean, kind of the spin can also heal, right, by reacting dynamically in my cartoon, which I completely neglect in this cartoon. But what you get if you assume this is basically that this doublon should scramble the spins in some localized vicinity around its basically position. Why? Because of the energy growth the further it moves away. So it cannot scramble everything. It should scramble a localized area. And that shows you basically that what you intuitively would expect is really the picture of a polaron that is created around that doublon, and that now can move only by what I said we neglect, right? By healing the spins where along its path and dragging this cloud of this destruction around itself with it. And this has really been has been studied in the early 1990s, late 1980s of the last, I said 19 of the last century, right? And that was really coined the magnetic polaron. And what we are not looking at here, and this is now very important to understand, the experiments I'm going to present you now is not about the properties of the polaron as a quasi-particle. So normally you think, measure the enhanced mass of this object or whatever, measure whatever participation ratio or something like this. What we do is we look basically inside the polaron. We look basically what is the magnetic structure inside that polaron with our microscopic resolution. And how do we do this? We now need to get our technique. Here comes now the imaging technique that I promised, version 2.0. So how do we get this technique to 2D? Well, we don't do much. We just allow now tunneling in the vertical direction, even though the distance here is still twice. So we still have the space to do the same superlattice trick as before. For this, we have to pay a price. It makes, first of all, our system only half the size in the vertical. And second of all the atoms, when we prepare this system, they come from a 3D isotropic cloud. So they have to heavily reorder to basically have half of the atoms only vertically than horizontally. And that costs us temperature that we can reach. And this is already an introduction to version 3.0 later. So it costs a price if you do it like this. But nevertheless, we can use our imaging technique and do 2D spin resolved microscopy. And now my usual joke that works better, of course, if you have an audience, is try to find the doublon. So maybe I give you 3 seconds to find the doublon. 1, 2, 3. Okay, no, the doublon is here. So this is one side which is actually doubly occupied, where you see basically in both cells we have an atom, and by that we can now basically calculate correlators between that site where we have the doublon and a magnetic bond. And the whole rest of the talk will be about correlators like this. So it's important to understand these kind of correlators. It's about a combination of charge and spin correlators. And the distance that we use is the distance between where does this charge sit and where's the center of that spin correlator. So this distance can be quite large, and we still have a nice spin correlation, even though the correlation length in the spin is short, because of it is always a short distance spin correlator only involved in this. So this is important. So this distance might be 5 sites, whatever, but this is not a long range spin correlation we are talking about. Okay. So now we can use this correlator and analyze basically the system. So first of all, what I show you here now in these plots is basically the black dots are the positions of the atoms, and the bar is basically the magnetic bond strength. And if it's positive, it is basically ferromagnetic, like aligned. And if it's negative, well, it's anti-aligned, right? So if we look at the diagonal bond in such an antiferromagnetic model, this I always have my problems. So the diagonal bond in such an antiferromagnetic model, if it's fully filled, you see it's aligned. And this is what we see if we go far away here from the position of the doublon. But you see near the doublon, we get actually a flipped correlation here. So the doublon really messes up the spin, and it messes it up so much on this diagonal correlator that actually the correlation flips completely compared to the doublon not being there. And this change of correlations is also true if we look at this next nearest neighbor correlator here, and you see basically this enhancement of negative correlations around that doublon here in this square here. Now we can of course make this more quantitatively and try to find a measure for the radius of that polaron. So how big is this guy, right? And for that, basically, we azimuthally average those correlations to get basically better signal to noise. And what we get then is shown here with basically the first thing to look at. So here you see the correlation strength, here you see the distance, right? So we go radially out. And here you see basically the background correlation level. You see basically that our data goes nicely to the background correlation level for both the diagonal bond correlator and for the direct bond correlator on similar scales. And so if you read from that, the polaron radius is somewhere between 1 and 2 sides. So this is this idea of looking inside really the structure of the polaron. And I should say, there have been very nice, very similar experiments done with relying on a statistical analysis instead of this microscopic resolution thing of spin and charges in Markus Greiner's group by Christy. I think Christy is also here in the team. So this was really 2 works in 2020 that went along together very nicely. Good. Maybe a stop here.
Cool. Yeah, let's take 2 quick questions here. So the first is about just on the 1D section. When you have spin charge separation, how does the hole and the spin, do they have dynamics that are different? Or should
the time scales are different, right? It's J, one is J, one is T.
Yes, but is it basically that they otherwise undergo just a quantum random walk? That is.
Good question. Yeah. Now let me go back for that, even because I skipped over that in the interest of time. I made a little note at the beginning that it's not so easy to track the spin because of the correlation length is not long. Correlation length is not long means there are many excited spinons above ground state in the system already, right? And the fact that there are many spinons already renders basically the spin motion incoherent. You see, you don't see anything here. While the whole motion does exactly what you asked, does basically continuous coherent random walk. And that's because of the charge degree of freedom is really cold because we prepare the system basically on the mod gap more or less. So you really don't have much holes in the system, but the spins, they are not gapped, and there you get a problem then.
Got it. So another question is, in the 2D experiments, presumably you're exciting a superposition of polarons at different k vectors and energies. Can you extract from, given that you have this large distribution, can you actually extract from that the polaron dispersion by looking at the correlations of the polaron versus time?
That's difficult, I think. So what we could hope for is extracting something like the effective mass of the polaron, means basically, right, the polaron dispersion in this way, what would it lead to, right? If I somewhat measure where that polaron is, if I would really, would it go, it would somewhat, it would disperse, right? The wave packet that disperses. So, but you could imagine basically preparing somewhat inner harmonic trap, or it would, this is in the end is a charge, right? So it would react to the trapping potential. So you prepare basically your charge in the edge of the trap, and now you try to let it oscillate, and by that, for example, measure its effective mass, its effective frequency. But really mapping out the dispersion, I think you have to do it spectroscopically.
I see. Okay, thanks. Okay, let's keep going then, Christian, and then we can have some more questions.
Keep going. Okay, good. So let me see, and not to jump. Yeah. Okay. So it's actually the last chapter now of my talk, and the last chapter is now moving along that doping axis in 2 dimensions, which is actually theoretically, probably from the theory perspective, the most interesting set of experiments, because of this is now really moving into territory that is not easy to be simulated. It's not impossible to be simulated still, but it leaves basically this demonstration of fundamental effects kind of a mindset that I've shown you so far, and moves into a little bit into uncharted territory. First, for that, imaging 3.0. Imaging 3.0 is now, now the motivation behind developing this thing is to get rid of this double spacing in the vertical direction. And what we do is, to do this is basically we separate the atoms and the spins here it's shown basically for the atoms in the imaging direction. So we had this single plane, we had the microscope looking from the bottom, and now what we do is we move basically, let's talk already about spin ups and spin downs, even though this is not spin resolved. What we do is we move the spin ups here and we move the spin downs here, and then we have two imaging paths after that objective. That one imaging path 1 is focused to this plane, and imaging path 2 is focused to this plane simultaneously. So this is the trick that we use now, and this is basically what I just said. We have like two paths with different path lengths, different lengths, and with this you can actually then displace on the same camera the cloud in this one plane and in the other plane. And you get the spin information encoded without having to do it without having actually to pay any price on your physics system that you have in your 2D plane. And here it's shown actually for a bilayer Hubbard system. We also studied bilayer Hubbard system, actually results that we never published only in a PhD thesis. Bilayer Hubbard systems that you can also separate in this way. Where we can basically reconstruct the double occupancies and all kinds of things here, and we can do that. That is basically what I described already on that in words and in drawings on the last slide. We can do that also for spins. So you have now initially basically a spin mixture in one plane. You do this Stern-Gallacht trick in the vertical. And then you move basically the two planes. By the way, that is a kind of trivial Taulas charge pump that we imply that we use here. So it's actually even a funny application of a quantum driving cycle to separate these two atoms, these two atom species, if you want, spin species, and then we get these images, and of course we can reconstruct basically the spin distribution in this 2D plane. So this is the technology that enabled now the experiments that I'm gonna present you now. These are these experiments there where we move now, what I said already, move in this direction. And with this, we were able to reach actually lower temperatures. This is this penalty that we had to pay on the distribution, redistribution of the density after loading. And maybe I think this is the only time I mention really a temperature. I should say our 1D temperatures are very similar to those. And you see temperatures we reach are, well, they are never really cold, right? Also not in hopping. So it's like half a hopping, and it's like 0.9 or something of the spin degree of freedom. Especially that means that the spin is really saturated. It's almost at very high temperature. Let's call it very high temperature. And because of this, is really now a benchmark for theory. I should say again, to be honest, it's not a benchmark for like state-of-the-art quantum Monte Carlo. You could simulate what's going on, but it's a nice benchmark for effective theories, and that's what we use the system to. So we compare basically our result to exact diagonalization, to effective perturbation theories that are valid at large doping. Of course, the Fermi liquid is also somewhere at very large doping. The non-inducting, even non-inducting fermions, I think 3 fermions we compare to, and to resonating valence bond like models, 2 different incarnations of those at small doping, so somewhere here, actually that are valid somewhere here. We compare them always in the whole range, and also to this string model of Fabian Krust and Eugene Demler. That is valid, also should be valid somewhere here. So these are all effective models that give you some kind of insight and make this problem treatable in certain regions here. But let me focus again on the experiments. This was just a short explanation what curves you will later see. So first, when we now move away from half filling, the question is, what does the magnetic order do? So magnetic order, you can either measure, as I showed you before, with standard 2-point correlations, or you basically can can sum up all the 2-point correlations with the wave vector of that it corresponds to the basically you do a Fourier transform, right? So you do a Fourier transform and sum all the components up, and that gives you the static structure factor. And that static structure factor we measure, and we measure that in doping dependence. So this is what's shown here. So you have the Qy, the Qx here that you get from the Fourier transformation, and you see the experimental signal here and in arbitrary units, because of there's a normalization to basically show the signal here. We also we kill the Q equals 0, I think in this. Yes, we kill the Q equals 0 to make this more visible. So it's about the structure basically in momentum space, and not about the amplitude, what we are doing here. And then you see basically with increasing doping, so you see here the doping levels is pretty heavy doping. So this is 0.5 doping, like half of the atoms in the system. We see basically that peak smears out. And then we see something very interesting happening. We see new peaks appearing. So we see peaks appearing at wave vectors that are incommensurate with the lattice. So we're seeing really incommensurate magnetic correlations appearing here. And of course, we can also do that more quantitatively, basically moving through a path like this through the polaron zone. You see basically the data here, and we put actually this TPSC. This is one of these perturbation theories on it, and we see that makes really a nice match. And I should say, in that paper I was talking already about in Markus Greiner's group, where they actually implemented this entropy redistribution trick to get colder, and they got colder than we are. They also studied basically this static structure factor, but they stopped basically at rather low doping levels. So they somewhat stopped here. So they kind of see the smearing out signals, but they don't see basically didn't measure to basically this incommensurate point that we see here. So that basically, so our measurements basically build heavily on the ideas that were developed in Markus' group here. Okay, so these were bulk observables, right? Well, bulk observables created from microscopic observables that we have. But we can also now look at really more complicated observables. And let me stay here for the sake of simplicity with the correlator that you know already. So our whole spin-spin correlator. So what I show you here is now the plots that you are already familiar with. So we have, in this case, a hole. So this is this confusion I was talking about before it was doublons. A hole and the different spin correlators around it. And what you see here at low doping is this polaron signal that I was arguing about already and telling you about before. And we see now basically that when we increase the doping, that polaron signal really drastically changes. So let's look at 0.5 doping. So this positive correlation that we have here on this nearest neighbor bonds, on this the nearest neighbor bonds, really changes sign and goes to negative. And what we always calculate here, this correlator, a bit for the experts, is always a fully connected correlator. So what is out of the correlator is any contribution of a 2-point magnetic correlator. Meaning basically, if this thing has the opposite correlation than what you would expect in the background signal, then that really means that this correlation is flipped by the presence of that hole there. And if we basically use that information and make that clearer, we can basically make a graph that shows you that is such that, it is such that constructed such that when these points, which is the strength of these spin correlators for different distance, right? This is again the middle of the correlator, which is the distance that is given here. And it's constructed such that it is positive when the spin correlation that we measure is opposite to what you expect for a standard fully filled antiferromagnet. And then what you see is basically that in the low doping, we see until, let's say, maybe, I don't know if you want to judge this point there, this I leave to you. We see basically everything flips basically. This is this polaron signature, right? It mixes up, it really messes up the spins. But when we increase the doping, we see basically that polaron signature goes away. And the only thing that survives is this very nearest neighbor point. But the signature at further away really dies. And now we can basically, to make this again more quantitatively, we now look at that point where we have the best signal, right? and track that versus doping, and that is what is shown here. Well, I think it's 2 points that are shown. Well, so this one here is the first point where not much dramatic happens. We see a little bit the amplitude changes, and this point which really changes sign is this correlator here that is illustrated here. That really makes this change from being polaronic, right? So it has this opposite correlations here, and then being at the same sign that it also asymptotically has in the Fermi liquid. So if you want to call something very roughly the bound where basically polarons die, then you could say that might be where that correlator changes sign and goes away from the value it has from the polaron side to the Fermi liquid side, so to say. So it's basically what I say is the whole doesn't mess up the correlations enough anymore from this point on. Yeah. Okay. Yeah. So maybe not to. We have different theories in the background that match more or less or less depending on which theory you have. But I think I don't want to go into details here and leave it on that level of detail I was so far. So summary. So I took you through a tour of what I think emphasized enough are so far hot Fermi-Hubbard systems in 1D and 2D. In 1D, we talked about the string order story, and we talked about spin-charge separation. Dynamically, string order was also an incarnation of spin-charge, as I said, separation, as I told you. In 2D, we basically did the analog experiment. So the string order story in 1D turned to the magnetic polaron because of there's just no separation that you can build such a string order. Then we looked basically at, right, that there's no analog to that. We basically looked at this polaron to Fermi liquid crossover. And now what I promised already, what are the challenges of the future? We discussed already challenges getting colder. I talked about that we want more control. Well, one thing is better local control. You could imagine really programming unit cells on that with your laser beam, right? If you really would have like an optical tweezer, individual control, but for that we need a very good quality of the potentials, which is hard to achieve. We are working on that. And the other thing is really this programmable hopping, programmable interactions. And I think what I already mentioned, Wasim's Rydberg tracing experiment that have been published very recently are the first step to programmable interactions in these systems. Leaves me to finish by thanking and really acknowledging the team. So that's the team of the fermion experiment at MPQ. By now, actually, the team is pretty much renewed, but I show the people that are really involved in the experiment that I've shown here. Yeah, and basically in some I could highlight everyone for some part of these experiments. It was like 3 years of experiments or 4. Funding, not to mention, remains, because now it's here. What's now 20? It's 10 p.m. basically now here and in Europe, and specifically it's in Germany. So let me say danke, thank you in German, with atoms in optical tweezers. So what you see here is basically these letters created with individual potassium atoms in our other experiments with optical tweezers. Thanks.
Awesome. All right, so we have definitely a number of questions here. Maybe to start, it would be appropriate to discuss this questions about cooling, since you were talking about hot fermions. The first question is, could you use the second layer as an entropy reservoir? So, yeah. And is this something?
The short answer is yes. That's exactly what the team of Jan Weipan has done in their system. Yeah. So you imbalance them a little bit. That one is basically in the metallic phase. Yeah. So you have a lot of and you also have, you have holes, and that's a lot of there's a lot of entropy capacity. And the nice thing with the layer is you have a coupling over a surface instead of over an edge if you do that in a single layer, right? So you have just better contact.
Yeah. Are there challenges there with ensuring that the basically you need to have a condition where the coupling between the layers is a small perturbation on the Hamiltonians within each layer?
such that you don't get effective hopping via the new layer, right?
Yeah, exactly. Or just
yeah.
scales of each of the local Hamiltonians, you don't want to be affected by this coupling.
Yeah, not to say that it might be interesting by itself, right? To have mediated hopping via the other. Yes, but for sure, you have to look. I think you have to look at in detail about on the timescales what you get. Yeah.
Okay, and then a related question: is there some way of designing an adiabatic demagnetization like cooling cycle in your experiment by coupling and decoupling the spin and charge degrees of freedom?
Yeah, but of course, in bulk, that also has been done already for cold atoms. I think in Wolfgang Ketterle's group, I think they have experiments on demagnetization cooling, right? Not that I know that anyone is designing that at the moment. So one would have to think about the protocol. Maybe it's possible.
Sure. Then another question is there a simple conceptual picture for why these incommensurate peaks arise?
I guess on that level where we see them, now I have to be a bit careful. On that level where we see them, my intuitive picture would be, so first of all, these peaks are broad because we are hot, because correlation lengths are short. So I think you can, on this level, probably you can still understand that as basically increasing on average the distance between the spins simply. And then the question is, why does this not mess up completely, of course, the magnetic correlations? Well, it messes up the magnetic correlations. They are much weaker. You need a lot of more statistics basically in this regime here than in the low doping regime. Yeah. And we are never talking. So I'm not claiming that these here are really that this is magnetic order. That is why I said that, right? So I think the story might be very different if you get colder, because of then what we are sensitive to is really the short range part of the correlations.
That's it.
Yeah.
And then maybe you showed us version 1.0, 2.0, 3.0, and then naturally you might ask whether is 4.0 going to be something that actually is for a 3D lattice? Have you considered whether this kind of system might be extended accordingly?
You could imagine, right? I mean, there's one simple way of where I would simple. You saw what I mean. What is simple, right? On one slide, yeah. So there's one simple way where how you could get that, at least with existing technology, to 3D. If you would do your experiments in 3D and then simply look only in the end at a single 2D layer, you could just basically blow away all the atoms that are not in one layer and then just use the same techniques that we have here. Then at least you don't have the trouble that you have so many atoms out of focus when you do your image. This is, of course, a big problem. And this is already a big problem that we are fighting every day in this technique here. Yeah? So if we go to very big systems, the biggest we can do, then actually we are having quite some trouble because of the background comes up, because of the atoms are not far enough out of focus. Maybe, I mean, if you squint your eye, maybe you see it even that there's a bit of background from the other layer on that picture. Of course, we separate them as far as we can to make that blurry as possible, but you always get some effects there.
What is the fidelity with which you can preserve an atom that's moved to a different?
If everything works, as I said, it's heavily dependent on the. First of all, you need very good performance of the experiment. Everything has to be well set, because I mean everything I didn't talk about. The laser beams to do this here with the fermions are extremely small that you need to do the imaging. Small means like 50 microns or something like this. And we are separating them here. Here, the number is even here. I don't have to see by 21 microns. So we are already moving really out of the central area of the spots. And of course, I mean, this is 3 laser beams, 3 pairs of laser beams. So everything is extremely critical to alignment. So if everything is nicely aligned, and if you have systems that are as big as shown here, then you get maybe histograms for your single atom distribution that are very similar with a slightly, so this is basically one plane only, maybe it's a bit better, and you get a slight enhancement here, which ruins your fidelity to, I think we have 95.
Yeah.
95, 96. But again, it is kind of painful keeping the system there. It easily looks like this.
Got it.
Yeah.
Okay. It looks like John has a question about cats, but I think maybe we should skip that. So, Christian, thank you so much. That was a fantastic talk. If you wouldn't mind unsharing so I could just quickly announce upcoming talks.
Okay, wait, I stopped sharing. Stop.
Good. All right. So is this working actually? It looks like it's not on my end. Is it working? Can you see my PowerPoint? Okay. So next week we have 2 seminars as usual. So the quantum science seminar, actually run by Christian, will feature Marcus Aspelmeyer on quantum optomechanics. And then our VAMOS seminar next week will be given by Jack Harris. Great, thank you. Let me remind you that the post-VAMOS discussion should be posted momentarily, I think, in the chat, and will also be posted on the YouTube if you'd like to discuss with Christian further his talk. Thank you.
Cool, was fun.
Thanks, Christian. Great talk.
Yeah, great talk.